there's one feature that we can observe from this game. So now, if we look at a pair of each cells, so this is 1, this is -1, -1, -1, 1, -1, -1. Oh, so this should be 1 here. Okay, so now actually my gain will be your loss, right? So this, we call this zero-sum game. Payoff add up to 0. So it is a situation that my gain necessarily means your loss, and your gain necessarily means my loss. Okay, so that's one feature. We call this type of game zero-sum game. Okay, let's analyze the outcomes. Analyze this game. So we're going to find Nash equilibrium. Nash equilibrium. Okay. So we need to check what is the Nash equilibrium. It's the equilibrium where that given the other player's strategy, nobody has incentive to deviate. So we need to check each outcome, each possible outcome, to see whether anybody has incentive to deviate or not. So this says, given B head, will A deviate from head to tail? No, because deviation is going to reduce his payoff from 1 to -1. Okay, given A head, will B deviate from head to tail? Yes, because deviation is going to increase his payoff from -1 to 1. So this is not. This is not. Well, this says check similarly, using the similar steps to check whether it is a Nash equilibrium or not. So given B tail, will A deviate from head to tail? Yes, deviation is going to increase payoff from -1 to 1. So this is not. This is not. Okay. Follow this says. Okay. Similarly, given A tail, will B deviate from head to tail? No, because deviation is going to reduce his payoff from 1 to -1. Given B head, will A deviate from tail to head? Yes. So this is not a Nash equilibrium as well. This says. Okay, this says given B tail, will A deviate from tail to head? No, deviation is going to reduce tail from 1 to -1. Okay, given A tail, will B deviate from tail to head? Yes, deviation is going to increase its tail from -1 to 1. So this is not Nash equilibrium. So now we don't have Nash equilibrium, or more exactly, we don't know pure strategy. Nash equilibrium. Pure strategy means that you choose a certain action for sure with 100 probability, 1 probability 1. Okay, but I'm going to tell you that there's a mixed strategy Nash equilibrium. Mixed strategy means now you are going to say mix your strategy up. Say I'm going to have 50% probability of playing this, 50% probability of playing that. Okay, or 30% probability of playing this, 70% of probability of playing that. Okay, so now we want to check whether there's mixed strategy Nash equilibrium. Okay, mixed strategy means that we are going to choose as action, mix up the actions. Okay. If you are doing BX2021, you can. This is not required for you. It's optional. But for EC5204, this is a compulsory. This is compulsory. EC 5204. Postgraduate one. Okay, so now let's say, so what we want to do is solve for a mixed strategy large equilibrium. Okay, let's say what we are going to do is A is going to be using alpha probability playing head, and that means 1 minus alpha probability playing tail. Similarly, B is going to have beta probability of playing head. That means 1 minus beta probability of playing tail. Okay, so now if I'm to play A, I want to mix up my actions here. So that's my mix. That's why it's called mixed strategy. Okay, I'm going to mix up my action. So clearly, I got to mix that for A, A got to mix the action, head and tail, such that here's very important way to solve the this mixed strategy equilibrium, such that B is indifferent between playing head and playing tail. If I didn't mix my action such that B under A, if I didn't mix my action such that B is indifferent between head and tail, then B is going to choose either head or tail for sure, and which means that my mix failed. So it got to be this. Okay. Then we got to say what's B's expected. B's expected payoff of playing H. Okay. So this is equal to what? So B's expected payoff of playing H. That means B, if B play H, then clearly there's our chance that he's going to end up in this cell taking a payoff of -1. There's 1 minus alpha chance that he's going to end up in this cell and having a payoff of 1 minus alpha. So there's alpha chance. There's alpha chance of getting a negative payoff, -1 payoff. There's 1 minus alpha chance that he's going to get a payoff 1. So now this is equal to negative alpha plus 1 minus alpha. So it's equal to 1 minus 2 alpha. So B's expected payoff of playing H is 1 minus 2 alpha. Okay, then we need to calculate B's expected payoff of playing tail. What is B's expected payoff of playing tail? Okay, if B play tail, then there's our chance that he's going to get a payoff 1. 1 minus our chance getting payoff of -1. So there's our chance of getting a payoff of 1. There's 1 minus our chance of getting a payoff of -1. So it's alpha minus 1 plus alpha. So it's 2 alpha minus 1. Okay, so now these two expected payoff must be the same. Because otherwise, if this one is bigger than this one, if B's expected payoff playing H is bigger than this playing tail, then he's always going to play H. Then my payoff is my mix will fail, will break down. Okay, so we need to have this expected payoff equal to this expected payoff, which means 1 minus 2 alpha. is equal to 2 alpha minus 1, which means 4 alpha is equal to 2. Alpha is equal to 1/2. 1/2. So alpha is equal to 1/2. 0.5. So A's mixed strategy should be 50% chance of playing head, 50% chance of playing tail. Okay, that's for A. For B, similarly, for B. So he is in exactly the same way. He got to mix the head and tail such that A is indifferent between playing head and tail. So now we need to calculate A's expected payoff of playing hedge, playing the tail. Okay, what is the A's expected payoff playing hedge? So if A playing hedge, then there's a better chance that he's going to end up in this cell getting a pair of 1. 1 minus better chance of getting a pair of -1. So there's better chance of getting a pair of 1. There's 1 minus better chance of getting a pair of -1. -1. Okay, so which means beta plus -1 plus beta is 2 beta minus 1. Okay, so that's the expected pair, A's expected pair of playing hedge. Then what is A's expected pair of playing tail? So if A play tail, then there's a better chance of ending in these cells, which getting a pair of -1. There's 1 minus better chance of getting pair of 1. So there's a better chance of getting a -1 pair. There's 1 minus beta chance of getting a pair of 1, which is equal to negative beta plus 1 minus beta. It's 1 minus 2 beta. And clearly, B got to mix his head and tail such that A is indifferent between head and tail. Okay, so which means 2 beta minus 1 is equal to 1 minus 2 beta. So which means 4 beta equals 2, beta equals 1/2. So clearly beta is equal to 0.5 as well. So now the mixed strategy Nash equivalent for this game is A, 30% chance of playing hedge, 50% chance of playing tail. B, 50% chance of playing hedge, 50% chance of playing tail as well. So that's the mixed strategy Nash equivalent. So this sort of game tools is widely used in addressing the situations where we have strategic interactions. And for our subject purpose, we only cover strategic form games. You need to be able to set up the games, be aware of elements of the strategic games, players, actions, and the associate payoff. After you're setting up the games, you need to analyze the equilibrium outcomes. To analyze the equilibrium outcomes, you can look for the dominant strategy. What is the dominant strategy? It's the strategy that you are going to use no matter what your opponent does. Okay. If both players have dominant strategy, then the outcome is certainly the dominant strategy equilibrium. Clearly, not every game has dominant strategy equilibriums. So we need to check for Nash equilibriums. What is a Nash equilibrium? It's a situation where, given the other player's strategy, nobody has incentive to deviate. So to check for the Nash equilibriums, we need to check each cells to see whether the condition is satisfied, to see whether there's anybody has incentive to deviate given the other player's strategy. And doing so, we are actually looking for pure strategy logic equivalence. Again, not every game has a pure strategy logic equivalence. So, like this game, matching penny games, there's no pure strategy logic equivalence. But players can mix up their actions, and there exist mixed strategy logic equivalence. To solve for mixed strategy logic equivalence, you now need to follow this step as in here. It's quite mechanical actually. So you got to mix up your actions such that your opponent is indifferent between his actions. So for B, for example, for B here, you got to mix up his head and tail such that A is indifferent between playing head and playing tail. And this way you solve the mixed strategy logic equivalence. Solving for mixed strategy logic equivalence is not required for undergraduate students, but it's required for postgraduate students. Okay, that's for this week. See you next week.